We have to show by using mathematical induction that the following statement holds true for all n. So first we're going to show P1 statement, then we're going to show Pk statement, and then we're going to show Pk plus 1 statement. Okay, just show. We're not proving anything, we're just showing for now. So P1 stands for the first term because there are n terms on the left side. As you can see, this is the nth term. So the first term is when the n value is equal to 1. So 1 to the third on the left side. I'm just writing the statement for P1. So 1 to the third only for the P1. And the right side will be evaluated at n is equal to 1. Okay? So 1 squared times 1 plus 1 squared over 4. We're just writing it out. We're not going to confirm it yet. We're not going to verify that. Pk's statement basically copies this down, except it substitutes the n with k. So 1 to the third plus 2 to the third plus 3 to the third until we get to k to the third, not n, we substitute it with k, is equal to k squared times k plus 1 squared divided by 4. In pk plus 1 is similar, except we're going to substitute k with k plus 1. So 1 to the third plus 2 to the third plus 3 to the third until we get to, instead of k, k plus 1. And be sure that you cube the whole k plus 1 and not just k to the third plus 1. Be very careful with that. Right? The whole thing is cubed. Okay, and that's equal to k plus 1 squared. Be careful here, you're squaring k plus 1 and not just k squared plus 1, right? K plus 1 squared. And then here, what we're going to do, we're going to write k plus 1 plus 1, okay, squared. Because k plus 1 is squared, you're substituting this with k plus 1 this case. So it's going to be k plus 1 plus 1 being squared, right? Being divided by 4. Okay, so now we're going to show P1 is true. That's the next step. P1 should be true. Because, why? Because the left side, 1 to the third is 1, right? 1 to the third is 1. And now let's confirm the right side. 1 squared is 1 times 2 squared divided by 4. And this is equal to what? This is equal to 1 times 4 being divided by 4, because 2 squared is 4, which is 4 over 4, which is 1, right? So we indeed show that the left side and the right side match, right? Both of them are 1, right? So that's good. Now assume Pk is true. This statement is true. Assume it. We're not proving it. We're just assuming that it's true. Because under this assumption, we're going to prove that Pk plus 1 statement is true. And then that's going to be enough. That's going to be the induction step that we take. So Pk is assumed to be true. So I wrote assumed twice. So I get Pk is true for arbitrary k value, right? So k acts just like the n here. N is going to be a natural number or a whole number. In this case, k is going to be some natural number, right? So for arbitrary k value. Then, if Pk statement is assumed to be true, we can basically rewrite Pk plus 1 statement in the same fashion. So basically, we're going to show that 1 to the third. Let's name that as Pk plus 1 statement. So 1 to the third plus 2 to the third plus 3 to the third plus, and then since we're working under the assumption that Pk is true, we have to finish writing Pk left side, right? K to the third, and then introduce one more term so that we're talking about Pk plus 1 under the same assumption for the Pk. Right, so it's going to be k plus 1 to the third, right? So basically we're copying this last term here. Is equal to this side, right? Let's make it look like that. So this is going to be what? This is going to be k plus 1 squared times k plus 2 squared, right? K plus 1 is k plus 2 divided by 4. Okay? So now we're going to study two statements, this one and that one, pk and pk plus 1. Notice that the left side is everything on this side until this guy here, right? These match. The only difference being that there's this extra term that shows to be the last term that is absent here, that is lacking here, right? So if we add this term to this left side, we have to do the same thing on the right side. Okay? So that will transform this statement supposedly into the pk plus 1 statement, right? So as a result, we can write so that pk plus 1 statement is going to look like this. 1 to the third plus 2 to the third plus 3 to the third plus all the way to the k to the third. Now we're going to add this one more guy to this statement. So we're going to do plus k plus 1 to the third is equal to, now taking this right side, we're going to copy it down, k squared, k plus 1 squared divided by 4, and then we have to add it, right? We have to add this guy to this side as well. So we're going to write it in red, plus k plus 1 to the third. That's it. So now what we basically need to do, now that the left sides match, okay, now that the left sides match, we have to make sure that these two sides match, right? Because the left sides so far match for the pk plus 1 statements, right? The left sides match, but the right sides do not look the same. We have to make them look the same. They may be the same quantity, but we have to show them. We can't just assume that they're equal. We have to make this, we have to transform this algebraically in such a way that it's equal to this. Okay? And maybe I should not circle that because we're going to circle that later when we transform this. Okay, so how do we do that? We do that by writing then the right side, this is the side I'm talking about, the right side turns into, let's see, so k squared, I'm gonna rewrite this again, copy this down, over 4 plus k plus 1 to the third. So now, obviously, this is going to be one term that we need to transform this into, right? So we have two terms. So we have to combine this into a single fraction. To do that, we have to have a common denominator 4 for these two terms, right? So that we're going to have to multiply this guy by 4. And then they safely can be divided by the common denominator 4, right? And you can check it back. 4 divided by 4 gives you the former coefficient of 1 that was there without the fraction. Okay? Then I see the k plus 1 term being common. We find the GCF. There's a square and there's a cube. Square is the greatest common factor, right? That we're going to have. Basically, a factor of 2 there, right? So we can put k plus 1 outside. K plus 1 squared outside. And inside, I'm going to have k squared, because it multiplies k plus 1 squared precisely, plus 4 times one more k plus 1 factor that was unaccounted for, right? Because the GCF was k plus 1 squared. So this has to be k plus 1 there under the power of 1 divided by 4. So now what happens is we get, let's see, k plus 1 squared, and this turns out to be k squared plus 4k plus 4, right? K squared plus 4k plus 4 divided by 4. The good news is that this turns out to be, notice you can factor this, this is a perfect square trinomial, right? That's the good news. So that means you can express it as a binomial being squared, which is going to be k plus 2 being squared, right? So you know k is going to be there, and then you're just going to take 1/2 of this, right? And write that number down. 1/2 of 4 is going to be exactly plus 2, right? That's how you find the binomial being squared to give you the perfect square trinomial if you went backwards from right to left. All right, so this is how you find that, and that's going to be divisible divided by 4. So as a result, look what happens. We did actually turn this guy into this guy. It's identical, right? We indeed showed that this can algebraically be transformed into this, which is exactly that. So this means that, and we can copy the pk plus 1 statement. We can say 1 to the third plus 2 to the third plus 3 to the third plus k to the third plus k plus 1 to the third is equal to the transformed right side, which is this, right? K plus 2 squared divided by 4. So this means that this statement holds true. Okay, thus this is a pk plus 1 statement. Thus, pk plus 1 statement holds true by principle of mathematical induction. As a result, right, by principle of mathematical induction, Pn, the original statement on the top, holds true for all n. So thanks for watching. Hope this was helpful. See you in the next video.